Okay, a couple things I want to add to our limit discussion. I want to just show you a couple little pictures here. Quick review, we've talked about limits, about the concept of a limit. We even invoked the calculus ants, a very helpful tool for understanding, what limits are really about. And keep in mind that limits, this is, if you have to say one thing about a limit, the mistake that people tend to make with limits is when you're taking the limit, there's this tendency for people to want that ant to take that last step. And with a limit, does he ever do that? No. We're just trying to determine where does that ant anticipate stepping. Where he actually steps is irrelevant as far as the limit is concerned. It's just where does he think he's going to step. And we looked at some examples yesterday at the end of class, and it seemed like people had a pretty good hold on that concept. We're going to move on here shortly and take a look at some ways that we can try to determine what a limit is analytically. So based on some kind of algebraic exact method, instead of having to graph it and just kind of estimate from the graph or make a table and interpolate from what the tendencies are on the table. But before we do that, I want to take one look briefly at a topic that we're not going to spend a lot of time with after this, but it's an important topic in calculus. We want to look at a more rigorous mathematical definition of a limit. And we're never going to use it, honestly. Or I wouldn't say never, but very rarely will we ever use this definition. But we have to be able to, when we put on our mathematician hats and we become mathematicians in this classroom, you got to think like mathematicians. And mathematicians insist that we know this works. Just because it seems like it ought to work and it's a nice picture isn't good enough. We have to be able to demonstrate rigorously that this idea of a limit, that it's a mathematical expression of a concept that we can guarantee to be true. Okay? So we started off yesterday just saying something like this, and this is what we'll continue to say. We'll write things like this. The limit of some function as x approaches c equals L, and L is just some number that that y is approaching, and that's how we're going to continue to write limits. And the way we say that, remember, is the limit of f of x as x approaches c is L. But we've got to attach some extra features to that definition. And so we're going to go back to what we call the epsilon delta definition of a limit, which was introduced a long time ago, a very rigorous definition. And here's kind of what it does. It makes this statement here. We say, if f of x becomes arbitrarily close to a single number L, we'll go back over this and talk about the language. This is a good example of rigorous mathematical dialogue. If f of x becomes arbitrarily close to a single number L as x approaches c from either side, then we say that the limit of f of x as x approaches c is L. So then we can say this is true. Now let's take the red part and the green part separately, and let's just kind of talk about that for a second. First, we'll talk about it sort of conceptually and theoretically, and then we'll go in and try to express it mathematically. What do you suppose that means? If f of x, we're talking about y values, right? If f of x becomes arbitrarily close to a single number L. Now there's a really important word there. Anybody care to suggest what that word might be? Arbitrarily. That's an important word. What does that mean? Say it again? Sort of. We're flirting with it a little bit. Arbitrarily. Comes arbitrarily close. What do you think? Does that mean specifically? What does the word arbitrary mean in regular language, just in normal conversational language?
Not necessary.
Maybe kind of, I guess it can connote that, sure. But it's arbitrary, meaning that it's not really pinned down, is it? Kind of in a way. Does that make sense? So random, I guess, in a way fits that too. in math, when we say something like f of x becomes arbitrarily close, it means we haven't made up our mind yet, right? We could make it, we could choose it to be whatever threshold we decide, and think of it almost as like a bullseye, right? If we're trying to, if this ant is walking along a function, and he wants to get, that's supposed to be an L, I don't know why that looks like a B. If he wants to get within a certain target accuracy of the y value that he thinks he's going to step on, that's what we need to be able to do with the limit, right? As he walks along this function, and as x approaches some value, and he wants to be able to anticipate accurately what the y value is that he's going to step on, he needs to be able to anticipate that as closely as he wants to, okay? So he can get arbitrarily close. I could get within a tenth of y, or within a hundredth of y if I want to, or within a billionth of a billionth of the y value that the function actually has, or that we anticipate having at that point. Does that make sense? So I've got to be able to zoom in on the y value. I've got to be able to anticipate with arbitrary accuracy, as accurately as I could possibly want to, where I think I'm going to step if I'm that ant. Okay, does that make sense? It's kind of a weird, ethereal concept, but that's what we're getting at. I've got to, if the limit is going to exist, the ant has to be able to, without any limit on his accuracy, anticipate where he's going to step in terms of a y coordinate. Okay? How's he going to do that? Well, if the ant is able to pick the y value, pick the limit with arbitrary precision, as close as he wants to, as x approaches c from either side. Well, you know that as this ant walks along the function, when he's far away from x equals c, he wouldn't necessarily expect his y value to be very close to the limit, would he? I mean, if he's way down here, for example, his y value is quite a ways off the target right there, right? He's that far off. Does that make sense? But as he inches closer and closer and closer, his y values are getting closer and closer and closer to the target, right? Make sense? If that's a tendency that always holds when you're close to that limit, then the limit works, okay? In other words, if he can increase his target precision, if he can get closer to the limit merely by walking closer to the x equals c value, then there's no limit on how close he could get, is there? Right? I know that if the door is the limit of my motion, remember we took that example yesterday, if I'm going to cut my distance to the door in half with every step, what's the limit of my motion? I mean, you tell me, if you just watch this picture, if I just keep doing this, what am I approaching? The door, right? I'm approaching the door. Where is the door? Well, it's right there, right? How close could I get to the door? Is there a limit on how close I could get to the door? No, there isn't, is there? Right? There's no limit on how close I could get to the door if I just keep taking those steps. So that limit concept really works there, doesn't it? Right? I could get as close as necessary based on the number of steps that I take. Just like the ant could get as close as necessary to his target y value just by inching closer to x equals c. Okay, that's what this is capturing here. That's what this is capturing. If we can get a relationship between those two concepts, getting arbitrarily close as we want to L, just by moving x closer to c, then the limit works. Now, there are some cases, as we discussed yesterday, where maybe that doesn't work, and we'll look at those a little bit. But for now, let's just see if we can take this language and turn it into some mathematical, analytical symbols. How do you suppose we're going to take this red sentence here, this red phrase, f of x becomes arbitrarily close to a single number L? Now let's just leave this example. We'll come back to it, but let's just leave this for a second. And let's just talk about number lines. We're gonna go back a little bit, maybe to algebra 2-ish stuff. Let's say we got a number line here, and this is, so there's 0, 1, 2, 3, 4, 5, etc. Let's say that we want to define an interval of points that are within a certain distance of 2. Let's say that 2 is my target in this case, right? I want to be around 2, but I don't need to be right on 2. Let's say I could be within 2 units of 2. What is that going to look like graphically if I want to graph all the points, the locus of points, we'd say in math, locus is just a set. The locus of points that are within 2 units of the number 2. We could just try some on the number line and see which ones work. Would the number 3 work? That works. How far is that away from 2? 1. So that would work. That would be in our set that we would fill in, wouldn't it? Does the number 1 work?
Yeah.
Okay. Let's say we could be 2 or less away from 2. Okay. No more than 2, we should say. Does 5 work?
No.
5 doesn't work, does it? 1/2 would, or excuse me, 2.5 would work. Would 4 work? 4 would work. Would 4.000001 work?
No.
It wouldn't though, would it? So 4 would be kind of an endpoint, wouldn't it? That's the furthest we could get to the right away from 2. What's the furthest we could get to the left away from 2?
0.
0. Okay, so then anybody want to hazard a guess or tell us what that's going to look like, that interval? Yes, sir. Say it again.
A line segment?
It's going to look like a line segment, isn't it? One endpoint at 0, one endpoint at 4. Now, where is it centered?
2.
Okay, it's centered on 2. What is now we might call this the spread. How far in either direction is this thing spreading out? 2. Okay, so maybe we could do something like that. Probably shouldn't use so many 2's. That wasn't a real good idea. You know what I'm gonna do? Real quick. Okay, same argument we just did, except just so I don't end up with so many number 2's, I'm going to center it on 3 this time. Just slide everything over. Okay, so 3 is going to be our center. There's the center. And the spread is 2. How's that? Okay. How can I say that mathematically? What are some ways I can say that interval? Okay, I could say this using inequalities, couldn't I? How many inequalities would I require? 2. Need to be a compound inequality, right? Would that be a conjunctive and inequality, or a disjunctive or inequality? Say it again. And, wouldn't it? Because it's got to be greater than this number and less than that number to be pinched in between, right? Remember, an or would look like ors on a boat, disjunctive, right? So this is an and. One way I could say this then is, if this is the x-axis, I could say x is greater than or equal to 1 and less than or equal to 5. That works. That works well. That's no problem. Is there another way I could say that interval? Really, the important numbers there weren't the 1 and the 5. The important numbers, I would argue, are the 3 and the 2. How come? So a little bit more fundamental in a way. Where are we aiming? 3, right? 3 is the target. And what's our target accuracy, plus or minus 2? So those are really the important numbers, aren't they? Right? The 1 and the 5 are sort of incidental. Just happens that that's where the boundaries end. Okay, and this works. That's not bad. But is there a way that we could express this interval in terms of those key numbers, the 3 and the 2? What do you think? I'm going to let you. This is important enough. I'm going to let you think about this for a second. At your tables, just see if you can come up with a way. I challenge you. Double dog dare you. If you come up with a way of writing this red interval in terms of those key numbers, the target and target accuracy. Okay, take just a second. See what you can do with that. Mathematical tools, and just can you think of any functions that deal with distance from a point, kind of a thing, or you know? Anything leap into mind, anybody? You guys are, yeah, your brains are churning. Now, you don't need to invoke anything two-dimensional here. This is just a line. All we need is just an x in it. We don't need any y's at all. We're just talking about x values. We'll try a couple things. And honestly, I don't want you thinking this is not some hugely important topic you're going to use a lot. It's really not. It's just sort of an interesting perspective on what mathematicians do sometimes. You know, I mean, but it's not very practical. First year calculus is really a pretty applied mathematics. We're going to end up using it to do lots of really cool stuff. We can use it to, just a little view forward here. We'll, very shortly, it's not going to be in the too distant future, we'll be able to do things like take a function and let's say we want to, we're launching projectiles and we've got a function that determines what the range of the projectile is as a function of angle of elevation, right? Well, we could use calculus very, very simply to determine what angle of elevation would we choose to maximize the range of the projectiles. That's one of the really valuable tools that calculus provides us. So it's very applied. We're going to be leaning towards much more applied things. This is not so applied. This is very theoretical. But it's a good example to kind of see how a lot of the stuff you've talked about in the past ties together. How it all really does sort of come to fruition when you start talking about calculus. Let's look at something real quick. Now, this isn't how I plan to do this, but this might be kind of a cool way to do it. If we want the numbers 3 and 2 to pop out of this, we've got a 1 and a 5 right now. Okay, now you guys talked about a plus or minus 2. Will this work? Yeah, it will. It will. Okay. What could I do? What number could I add or subtract to all parts of this inequality to generate a -2 on one limit and a +2 on the other? 3. What would I do to all 3 parts of this compound inequality? What number could I add or subtract to all 3 parts to end up with a lower limit of my -2 and an upper limit of my +2? I could subtract 3, couldn't I, from all parts? Okay, if I do that, I'm going to end up with a -2, an x minus 3, and a +2. Okay? And honestly, in math, a lot of times, these are if you don't know where you're going and you're trying to evoke these numbers, maybe that's something you do and to just try some things out. Now the numbers appear. What can we do with that? We got our important numbers. There's the plus or minus 2, right? The +2 and the -2, and there's the 3. Okay, so far so good. Is there an alternate way of expressing that compound inequality? Have you ever seen anything like that? Think Algebra 2, Honors Algebra 2. How could I rewrite that compound inequality without using inequalities? Or without using two inequalities anymore? Let me ask you this, could I rewrite it in terms of an absolute value? Could I rewrite that? Could I take this stuff and say the absolute value of something, what's this equivalent to? The absolute value of x minus 3 is, I think I'm hearing it. Now think about this, the absolute value of x minus 3, that's saying the distance of x from 3 in a way, isn't it? Right? The absolute value of x minus 3, if x were 4, what would that value be? 1. Okay. If x were 5, what would it be? 2. What if x were 2? It'd be 1 still, wouldn't it? What if x were 1? Okay. Right? And so that's keeping this distance. This is like saying the distance between x and 3 has to swing between -2 and 2, but because we've got those absolute value bars there now, I can just write it that way. Because it's going to make it always positive, isn't it? Does that make sense? Now that's really what I was trying to get at earlier. here's another way that we could express that interval, isn't it? Because when we write an absolute value this way, isn't this just saying, if you go clear back to probably algebra 1, isn't this just saying this is the set of all numbers where the distance of x from 3 is less than or equal to 2? So really it's just saying all the points on a line that are no more than 2 away from that center point, right? And in general, if we write an absolute value statement this way, oops, color code this. We'll call that A. Anytime we write something like this, we recognize that this is going to be the center of the interval, and this is really just the spread, right? So this is like an A, and that's like our C right there. Make sense? That works, doesn't it? Right? Okay, so we could use that idea then, and we could go back to our, why are we even talking about this? Oh yeah, it was this stuff, wasn't it? Right? We were trying to find a way of saying f of x becomes arbitrarily close to a single number L. Well, there's our target, right? The arbitrarily close, that's like this, how wide do we want the spread to be? In this case, it was 2, but it didn't have to be. We could have chosen it to be 1, or 1/2, or 1/100th, right? All that would have done is just, would have shrunk this interval down, right? So we can go back now and say something maybe like this, right? We could go back and say, all this stuff in red, really, we could say that mathematically like this. We could just go, the absolute value of f of x minus L is less than or equal to, do you want the less than or equal to there? How do they express it here in this group? Yeah, just less than. We'll say that it's got to be within this interval. Epsilon. And epsilon is that's just a Greek letter. We just chose that one arbitrarily. Epsilon is the variable. That's not a very good epsilon. Let me draw that differently. A lot of times we draw it like that. That'd be better. That's the target accuracy that we're choosing. We'll call it epsilon. Does that make sense? So the distance between the y position of the ant and the actual limit could be whatever we need it to be. Call it epsilon. There's our epsilon right there. How close do we need to be? Okay, make sense? As x approaches c, okay? Or as x approaches c from either side. Okay, so as we get closer and closer to c, well, we could say something just like that. We could say, as x approaches c, the distance between x and c would just be defined like this. We'll call that delta. Okay? Does that make sense? Questions? Right? What have we done? Didn't seem like we've done a lot. But this is a way we can say this thing now, right? So if we can make a connection, if we can show that this is true and that epsilon is connected to delta, then the limit exists, right? Okay, so it works in cases like this. And I'll put this little applet on the Moodle side so you can mess with this too. But let's just take a real simple example. Let's take y equals x squared, right? How close do we want to get? Pick an epsilon. Within 1. Okay, if we want epsilon to be 1, let's make it 1 here. Where is the... Well, close enough. So if I want kind of the red zone, right? If I want my target accuracy to be 1, well then how close do I have to be, does my x need to be, right? If my, if my target Y accuracy is going to be plus or minus 1, then doesn't that mean that if the ant is standing, how am I going to do this? If the ant is standing, give me 1 second here, let me do this. Ah, much better, okay. If the ant is standing, say, right there on the function, is he within 1 of his target Y value? Not, is he? Make sense? When he's standing right here, his X value is like 1 point something. His Y value, it looks like is, I don't know, what is that, about 3? Something like that. Looks like it's going 1, 2, 3, something about 3. That's 2 away from the limit of 1. It's not close enough. What's he have to do to get within the red zone? He's got to move. Where's he got to move? He's got to back up this way, doesn't he? Now, when he's right here, he's okay. Whoops. When he's right there, he's okay, isn't he? Then his Y value, if I look at his Y value, he's inside that red zone. He's within 1 of his target limit, right? And the limit's just 1, isn't it? I guess we should specify that. If I take f of x equals x squared, what's the limit as x approaches 1? Well, where's he going to step? When x is 1, what's the y value? 1. Yeah, he's going to step, so he anticipates stepping there, doesn't he? We can see that the limit is equal to 1. It's right there. Okay, well, what's the zone that he has to be within? We could check it out here. We can just go over and let's drag this delta to where it's just right. It's right about there, isn't it? Okay, he's got to be within plus or minus, the x values need to be within plus or minus probably, I don't know, what does that look like? A little less than 1/2, something like that. But as long as he's within this range of delta, as long as his delta is plus or minus a little bit less than 1/2, he's going to be in the red zone. He's where he wants to be. By the way, this is kind of a friendly way of saying this. In math, we say that this range of x values that gets us in the target red zone is called the neighborhood. If he's within a certain neighborhood of x, it's going to work. It's very friendly, isn't it? But what if we take that red zone, that's not accurate enough. We don't want to just be within plus or minus 1. Let's say we want to be within plus or minus 1/2. So let's make epsilon about 0.5-ish. Now look what happens. Now that spot that used to be in the red zone no longer is. He's got to get a little bit closer. It's going to take our neighborhood and it's going to shrink it down a little bit. Now the neighborhood has to be smaller in order to get our desired target accuracy. Make sense? If I want to get the target accuracy even tighter, what do I have to do? Just shrink the neighborhood down a little bit, right? Shrink down delta. Make sense? And no matter, there's no limit, no pun intended, to that process. I can get as close as I need to be. So the limit concept works perfectly well here. No problem at all, right? Now, I don't want to belabor this too much. Let's just go down to one example that doesn't work. Let's go down to that weird example of, actually I want to change this. Let's just do sine of 1/x like we did yesterday. Okay, there it is. Well, let's approach x equals 0. Okay, we're going to approach x equals 0. What's the y value at x equals 0? Well, where does the ant anticipate stepping? Who knows, right? It doesn't, in there somewhere, but we don't know where, right? And it doesn't help in this case if I let the neighborhood have a width of, let's say about like so. So there's can you see that little green bar? There's the neighborhood. That has, increasing or decreasing that slightly has no impact on my target accuracy. My target accuracy is something like that, no matter what. Because that ant is just oscillating around between -1 and +1 in there, just without any rhyme or reason, isn't he? There's no way that I can get that ant anticipating a specific value as he approaches x equals 0 that's any tighter than that, because it's just doing this, right? So does the limit work there? It doesn't work. It doesn't work because I can't get arbitrarily close. I'm stuck with that precision no matter how small I shrink my neighborhood. Get the idea? So our rigorous definition of a limit doesn't work. We can't do this trick anymore. Because no matter how much I shrink this one, there's no connection to the red interval. Okay? This, by the way, if I were sitting out there and I had an expectation of this being 100% clear, I would probably be very frustrated right now, because it's not going to be. Now, I wouldn't expect it to be. My goal here for you right now is just to kind of get, oh, I kind of see the concept there. You know, you'll come back to this many, many times in calculus. And each time you come back, you're gonna have a little bit bigger bag of tools, and it's gonna make a little more sense. But I just want you to kind of get that ethereal, that connection between the concepts of an epsilon and a delta. Okay? Make sense? Sort of, kind of, maybe? A little bit? Okay. Why don't, I think we can just call it quits there. I think that's good for limits, for the first section of limits.